Sup guys, welcome to today's show. So last time I went through the design of my own file system, ddosfs, and today we're going to start implementing it. And we're going to start by creating the disk emulator, which we're going to use during development. So we'll be able to use a disk even when running this on Windows or Linux or whatever system you're running. So first of all, I'm gonna start by creating one more modifier level. Currently my functions are either and the variables are either private or public, but I want to have one more layer which makes it internal, so it can be reached from the other internal functions, but it will not be a part of the public API and reachable from the command.com. So I'm gonna copy this public thing and I'm gonna call this internal, and I'm gonna change the visibility to hidden. I think this will work. I haven't tried it, but let's try it and see, because I don't want it to be a static thing, because then we won't be able to reach it outside of the file. And I want to put the disk emulator in its own .c file, but it will be a part of this OS API package or whatever. So let's create a new file. Let's call it disk.c, and it will accompany a disk.h. Let's modify the make file a little bit. So we will create a new production rule for disk.o, requiring disk.c and disk.h. We will run cc with some flags. And it will be pretty much the same thing as the thing above. Okay, so we will probably need to it would have been kind of nice if we could make one single file out of this API. We can, maybe we should make it a regular dynamic library. I wonder why I didn't do that to begin with. Is there some downside? Well, let's try. So we want to create an OS API.so, and we need the OS API.o and the disk.o. We want to run cc with a flag. Let's do this again. So OS API.so, and we need the os api.o and the disk.o. And we run cc with some flags and some more flags, and we need some, what we're going to call them, SO flags perhaps. And we're going to take in the input files, and we're going to create the output file like so. And what are these SO flags? Let's see if I remember. So we're going to need an LDL, and I think we need to do shared, and isn't it one more that I usually use? LDL shared. I do this far too well, not often enough. So let's see, let's go into here. Let's go into code and birch utils, and let's check this makefile. So fpic. So we make it position in independent code, like so. And I think when we use this, we can probably just need to update this makefile. So this will be SO and right. So we can add OS API disk.c, OS API disk.h. And then we can include the SO when we link. So let's just include stdio and disk.h. No, we only need this. And this is disk.c. Alright. Did I save everything? I think so. So let's go into the TMP and the OS API. No. The ddosfs, then the OS API. And let's set this to our home. And let's see if it still compiles. Let's update the clean part of it as well. And that would be inside of this makefile. So we need to also remove any .so. No, wrong file. Here we go. So star.so. Alright, will it compile? It compiled. Did we get an SO file? No, we need to put it inside of our all. Like so. Relocation in read-only section text. Why does that happen? Let's see if it works anyway. Will this still compile? Yes. All right. That's pretty nice. So now we have everything contained in one file. Alright, so how do we create a disk emulator? First of all, we need to have some data structure for the disk itself. So let's see. This will be a struct. Let me just double check one thing. So we haven't created any data structure yet. Let's also create one of those for packed. So packed means that it doesn't fill out with zeros to arrange alignment. So this will not be visibility, this will be packed like so, I think. So we will have a struct packed, and it'll be a public. No, this will be, what did I say? Internal. Struct packed. So this will be the struct disk. And let's see, what's this going to contain? From my video, I copied these things because I haven't written any official RFC yet. So we need an int32 for the file descriptor, which is backing this disk. We need to keep track of the maximum number of blocks. Is this attached or not? This will only be 1 bit. And then we need the drive number, which is an int 8. Right. So we will type def internal struct packed as disk. That's a mouthful. And we'll just call this disk. Alright. So the first thing we need is some kind of mounting function, or attach as I will call it. So this will return a disk, and I will prefix all my functions that has to do with the disk with a D. So this would be D attach, and it's going to take a drive number and nothing else, I suppose. By the way, do I really need this attached bool? Because this data structure will not be created unless it is attached, right? But I need somehow to keep track of if it is, or which drives that is attached. Let's see. Maybe we can do some temporary thing and make something better out of it later on. So let's see, if we create something like, let's make some definitions. So let's say we have a drive C, and we call this 1. And the D disk would be 2. So let's say we for now only support those two. And then we need to translate this, because the C drive usually is something like 0x80 and the D drive 0x81. But I want to store these inside of one single int 8, and they will collide if I use this syntax. So I think for now at least we will do it this way. Why are they complaining? Well, we'll see. Alright, so how will I keep track of which are mounted and which are not? We will have a global int 8. So this will be internal int 8 attached, like so. And I will also need some kind of initialization function. let's just do void dinit void. We can start with that one. So dinit. The only thing this will do for now is set this attached to 0. We will also use this one to actually do the attachments. So maybe we should start with the unattached or detached. So this will never fail, so let's make it a void and call it detach. And it's going to take in the drive number. Or perhaps it's going to take the data structure. So a disk star. And we probably only need 2 bits for this, at least for now. Alright, so if we start with the detach function, so void detach, and it takes a disk dd, that's disk descriptor. So let's first check that we do have a dd. If we don't, we could just return. Don't need to produce an error actually, because it won't do any harm if we try to detach. But if we do have an active one, then we want to modify our attached and remove that bit. Let's create a temporary variable. So x will be equal to, let's see, I need to see the actual bits. So let's say we have a 2, so we try to detach the D drive. So we will start by taking the DD drive number. And we want to invert this. So this will be 1101. And then we want to AND it with the attached variable. And that will be our new attached. So attached is equal to x. We could probably do this without an intermittent variable, but this is better, I think. It clearly shows our intent. And then we will simply free this data structure. and return. Alright, so we also need to decide where to put these files. Maybe we can create a directory here. So let's call these drives. Or disk maybe. No, let's do drives. So inside of our disk.h, I will create another definition. So let's call this base directory. Like so. Or maybe we can call it base path. And then we can put the file name as well. So this will be disk dot and then the drive number. So we need to somehow merge this string with a number. And we will not have access to snprintf, which I would have used otherwise. I will make my own snprintf and printf, but not yet, I think. So perhaps we can have some temporary function as of now. And let's also make all of these internal. So maybe we can make some simple function which will just add a number to the end of a string. So what should we call that? strnum perhaps. And maybe we should put that inside of our OS API, because we might need it. And maybe this disk.h should include the OS API as well. Or maybe instead OS API.h. So let's see. strnum should return a pointer to a string. So int 8 star strnum, and it's going to take an input string and a number. So let's see. So we need to put this inside of here. Internal int 8 strnum, and it takes a string and it takes a num. And I think we're gonna use a static buffer for this. So static int 8 buff 256. Let's zero out this buffer. And then we need to copy the string. Do we have a copy function? We probably don't. Do we have a zero function? That we do. Static void zero. Alright, it's here. But we need to create a copy function as well. So it doesn't need to return anything. And it will simply take in a destination, a source, and a length. And we need to create all of these things ourselves because we will not have access to the standard C library. At least not in the end. So let's create this thing, and this will be a private copy and void copy int 8 destination int int 8 source int 16 len. And we need an int 16n, and we need 2 pointers. So this is the destination pointer and the source pointer. And we will set dp equal to the destination, sp equal to the source, n equal to len. And we want to keep doing this until, or as long as n is non-zero. At each iteration, we want to increase dp and sp, and we want to minus the n, and we want to set the destination equal to the source. Easy peasy. Alright, so let's copy into our buffer. we also need to have a length function. So private int 16, and we can call this string len. It's going to take an int 8 star. So let's see. So private int 16 string len, and it takes an int 8 string. Int 16n, and this will be pretty similar to our other function. We'll have an int 8 p, do a for loop where we set p equal to the str, we set n equal to 0. We go as long as p is not 0, and we increase p and n, and then we just return n. So let's create an int 16n, and n is equal to the string length of the input string, and if n is 0, then we can just return the input string. Or maybe not. Or let's do that. Alright, so now we have, let's say the string is ABC. That would mean the length is 3, and if we add the indices, it will be 0, 1, 2. So let's copy into the buff the input string, and we want to copy n bytes. But then we need to add the trailing 0. So let's see. The 0 should be here at index 3, which is the same as the length. So buff n should be equal to 0. And then we should add the number. By the way, let's double check that n is not more than 250, let's say. In that case, we will return an actual error. Or we don't really need to actually. Okay, so how do we add that number? let's create a variable for that thing. So let's call it x, or maybe c. Let's also double check that num is not, let's see, it shouldn't be more than 9. Alright, so we want to turn these 0, 1, 2, 3, etc. into the character version of that, the ASCII character version. So if we do printf the number 0, that's 30 in hex. And what is 9? That's 39. Alright, so if we take the number and simply add 30 to it, we should be okay. So let's see be equal to num plus 30. Then we should just be able to add that at the end. So if we increase this afterwards, we should be able to just do buff n. Well, we don't need to add the 0 at this point. Let's do it the other way around. So buff n should be c. Then we want to increase the n, and then we can set buff n equal to 0, and we return buff. Simple enough. So how do we try this out? Well, let's make this public temporarily. strnum, so we'll go into here. So now we should be able to go into this right here. Let's create an int 8 star, and let's set p equal to strnum, and let's say we have drive dot as our string, and then 1, let's say, as the number, and we print this thing. Alright, let's see if this works. Alright, 17 side of osapi.c. Stringlen private. Did I make the wrong function public? I did, didn't I? strnum is what we are trying to get to work. Statement with no effect. Oh, that should be else if. Oh, I did the same thing here. Passing argument 1, 0 from incompatible pointer type. Static int 8 buff. Do I need to cast this? Expected blah blah blah. Maybe because I mixed the order. Let's do internal packed instead. Empty declaration. Oh, there should not be a semicolon there. Warning, visibility attribute ignored. So we should not have that inside of the type declaration. Which flag was ignored? Visibility. So let's do this. Pack. Okay, we don't need it here either. Free DD, implicit declaration of free. That's right. We don't have any malloc nor any free at this point. We will not have it in production either, but I am currently developing my own malloc function. So when it is done, I can use that instead. So let's for now use malloc, and then we will remove it later, replace it with my own. So let's see. We can do inside of OS API, I guess. Where is malloc? Man to malloc 3 stdlib, okay. And all of these will be removed in production. So let's see. So let's use the naming from my own implementation. So if we go here, so instead of free, I think I called it destroy. And let's go here and create some alias for that. So we'll have an alloc function which takes an x, and it will simply call malloc with that x. And same with destroy, we'll call free. Static but never defined. Okay, so that's because we include it from our disk, I guess. possiblt.c. We do have this library. Let's use that. So let's do if defined library. And if think this will work, but we will not have access to this then, will we? Maybe we don't need that. Okay, compiled. Let's see if it works. We also need to compile this thing. Implicit declaration of strnum. Right, since we made this public, we'll need to move it into the OS API. Which means we need to recompile this too. Warning, pointer target. Alright, we need to make this an int8 string. Like so. Alright, it compiled. Will it work? No. Okay, so it just returns this. So that probably means that one of these if statements in the beginning did not turn out as I hoped. So let's see. Oh, if n is 0. No. stringlen str. This will not be 0. And n is not more than 250, I think. And num is not more than 9. So why did it return the same thing? Let's print out n. And num. Okay, so n is 6. Drive dot 1, 2, 3, 4, 5, 6. Okay, that's right. And num is 1. So we have drive dot, and the length is 6. So we have these indices. Which means the 6th byte should contain the number. This should be 0x30. There we go. All right, nice. So now we have the naming done, and it took quite a while, but now we have utility functions for a lot of other stuff as well. So all good and well. And let's move this thing back where it's supposed to be. And it should be here, right? And this should be internal. Okay, so now we can go back to the disk emulator. The next thing will be this attach function. So let's see. So it's gonna return, and I always forget the modifiers. So internal disk star disk attach, and it takes a drive number. And if drive is equal to 1 or drive is equal to 2, then it's okay, but otherwise we return an error. And this is temporary. So we'll have a disk dd, and we need to have an well, let's do it like this. Int 16 size. We'll set the size equal to size of, and this is internal packed struct s disk. So dd will be equal to disk malloc size. If we don't have a dd, we return error. And we zero this thing out. Okay. So now we need to open the actual file, and we do need to have the file name. So let's do file. File is equal to strnum, and we take the base path and we add the drive number. Then we set the ddfd equal to open this file. And we're gonna make it read only. We need to have an intermittent variable, by the way. So let's make a signed int tmp. Set tmp equal to this, and if tmp is less than 3, because -1 is usually if it's an error, but then we have 0, 1, and 2, which are the standard input, output, and error. So 3 will be the first real file descriptor. So if TMP is less than 3, then we can free our data, or no, maybe we should. Let's do it like that. It's not perfect, but who cares? So we free this and we return an error. Otherwise, we copy this to our data structure. So ddfd will be equal to the int32 of tmp. Alright, so now we need to figure out how many blocks there are. And we have a predefined block size, which is 512. So if we figure out the size of the file and we just divide it by this, so there is a system call, I think it's lstat. No, it's fstat. So it takes an fd and then a struct stat buffer. Struct stat. Let's call it sbuff. Set tmp equal to fstat and we give it the file descriptor. And the address of sbuff. And if tmp, let's check the return value. On success, 0 is returned. So if tmp is non-zero, no. Let's see. If it's 0, it's okay. So if it's non-zero, it's an error. So in that case, we should free our dd. We should close. Maybe we should do this the other way around. We should close our fd. We should free our dd, and we should return disk star 0. Otherwise, this sbuff should contain the information we want. Man3 type stat. Here we go. So let's see. Number of 512 byte blocks allocated. That's pretty nifty. So why don't we just use this? So dd blocks will be equal to the int 16 of sbuff.stblocks. So now we have the FD, we have the blocks, and the drive number we can just copy. And we need to add this to our attached variable as well. So attached should be equal to well, it's going to be equal to itself ORed with the drive number. So OR equals drive number. And then we'll just return DD. But we do also need to check from the beginning that this drive is not already attached. So if attached and the drive number, then we should return an error immediately. And there we have it. Now we can attach. Or at least after we have fixed these errors. So strnum, didn't I change that? Internal. Internal. Didn't I save? Public 51os.h. Maybe I didn't say this one. Alright. Visibility attribute ignored because it's already defined. Okay, so we don't need it there. Implicit declaration of 0. So let's make the copy and 0 functions internal instead. Pointer difference in signedness. So make this an int 8. Can we do this inside of an H? Yes, we can. Alright, let's see if we can mount a disk. Let's create one first. So let's go into drives and we can do, let's see, how many sectors, blocks are we going to use? We want to use 65,500 and 35. So let's do dd dev0, and the output it's going to be drive.0. Block size is 512 bytes, and the count is this. So 33 megabytes, okay. So let's see if we can mount this thing. And how are we gonna do that? Well, let's make this dinit public for now. And let's create a disk. dd is equal to well, let's create two of those. So this should be equal to d-attach drive number 0, and let's do it for the other one as well. So this will fail and this will work, I hope. And then we can print the address of the return values. So this is disk 0. This will be like so. Something like that. Let's go to this and move it here. We should pass the data structures to dd and dd1. disk.h, forgot to save again. And there we go. Oh, we need to call it as well. So disk init, like so. I did not expect that output. This should be this. Or maybe we can just do this and this. Both 0. Oh, this should be 0 and no. Wait a second, I'm doing the wrong thing here. Let's make this 3 instead. Or maybe not. And this should be 1 and this should be 2, right? 1 and 2. No? Here it should be 0 and 1. Here 2. Okay. No, still doesn't work. Did it recompile everything? Let's do it like this. Make no, something is still wrong. Let's do an S trace of this. No such file directory. Oh, I named the disk wrong. This should be drive 1, nothing else. Still doesn't work. Okay, disk 1. There we go. So this is the pointer to the data structure of the disk, and the other disk does not exist. So now we can successfully attach a disk. We'll be right back after this. Alright guys, welcome back. So before the break we implemented the lion part of this file system or disk emulator. What we have left is the read and the write, which will be quite simple, I think. And I will also create a show function, which will show some information about the file system, or disk rather. So let's go into the H and define an internal function which will be called dshow, and it will take a disk descriptor as argument. So let's see, let's make a copy of this structure. So we have it easily available. And now we'll create the function. So it's going to be a void dshow, and it's going to take a disk descriptor. And if we have a dd, we're just going to print, let's do so fd, and we can take this as a regular integer. Blocks as well. Maybe we can add some kind of header as well. So drive and then the number. So if you're not familiar with this HHX, that just means that it's a 1 byte field. Let's also print maybe that's enough actually. So our arguments will be the drive number, and we need to make this a regular integer, or maybe a regular char. And then we have the FD. And the number of blocks. And then we return. Simple enough. So let's do before we detach those, we will do dshow of dd and dshow of the second one. So the first should return some information. Maybe we can remove this. And the second one should return nothing. Okay. The number of blocks became 0. Why is that? Let's also, by the way, print the 0x02hhx and the attached variable containing the, this one. But why didn't we get any blocks? Let's see, where do we get those from? We did get the drive number, which means this shouldn't have returned 0. But this still did. That's a little bit weird. Does it change the attached variable? Yes, it does. That's weird. Does it have something to do with the conversion into a 16-bit field? That shouldn't be it either. Okay, it's a long int. Oh, I changed the wrong one, didn't I? So okay, 36. Since the variable can only hold 65,535, it becomes 0. But I thought I made those 65,535. Let's check. History, grep, dd. Right. So it counts wrong. Let's check the file size. So it's inside drives, disk 1. So this is the file size. So if we were to take this and divide it by 512, yeah, it is the correct size. So we need to take -1 when we do this. Okay. What's this? Ah, that's attached. That's right. And let's print that. Twice. Let's print it after we have unmounted and see if it goes back to 0. Yes. Okay, cool. So everything works this far. So now we only need to implement the read and the write. And when we are dealing with the file system later on, these will be the most advanced of the functions to write. But in this case, it shouldn't be. This should be very simple, actually. But we do need to change one thing. This shouldn't be read-write. This shouldn't be read-only. This should be read-write. And I haven't never used the lc command together with read-write, but I think we can use it to write blocks at any position and overwriting just those blocks. So let's try that. So basically the API will be something like this. We will return a bool if the read or the write is successful. So we will have something like disk read, and it takes in an int 8. No, it takes in a disk. dd. It takes in a memory address, so something like int8 address, where we want to read into. And then we need the block number, so an int16 block number. Maybe we should define a data type for the block. So something along the lines of type def int8 block, and that's 512 in size. So now we can change this to block. And similarly, we will have a disk write with the same signature. But I am not going to define these as functions, since these are very simple to do, I hope. So I will make this a comment, so we have the signature here. But I will use a macro instead. So I will create a macro, which I'm going to call disk IO, which will either read or write. So it will take in a function, a disk, an address, and a block number. And it's going to do a couple of things. First, we need to check that we actually have a disk like this. So dd should be true. And then we want to do this lseek operation, or some point fseek maybe. Let's see, lseek. Okay, this takes an fd. So lseek it is. So lseek moves the cursor basically to some part of the file. So it takes in the fd, and then the offset where we want to land, and then some kind of constant which defines what we want to do. So we want to use this set. So we want to run lseek on the dd fd, and this is not dd, by the way, it's d. So on the dfd, and the offset will be the block size times the block number. And then we give the constant of this. And what does lseek return? Upon successful complete, returns the resulting offset. on error -1. So we need to do something like this. If this function is not equal to -1, then it's successful. And if that case, we want to continue. And we want to do one more thing, and this is the read operation. So we want to read or write. We want to run the f, basically, the f function. And the first one is the file descriptor as an integer. So it's the dfd. And we need to cast those things as well. And the second argument is the memory address as a char. So this will be the A, and then how many bytes we want to read, and this will be block size. And the read and the write operation both return the number of bytes read or written. So we want to check if this is equal to the integer value of block size. Or we can just do this. So if all these statements are true, let's see, this is this and this and that, then we return true. So now we can simply define our disk read. And now we just take in a D, an A, and a B. And we call our disk I/O with our D, our A, and our B. And same with the disk write. And we need to provide the function, which is read. And here we do write. I think this will work. Perhaps we need to define these afterwards. Now I think I removed the wrong thing. This should still be here. So define disk read with a D, an A, and a B. And it will call disk I/O with read D, A, B. Same here, only we change read to write. I'm not sure if it's possible to do this, but I think it is. It makes sense, doesn't it? So if we go into our disk, and first we attach the disk. Let's also create one block, BL, and let's initialize this to something other than 0. Let's say 0x90. And I'm not sure if you can use this syntax. I know it works for zeros, but I'm not sure. We'll see. So then we should be able to write to a specific block. Let's say we want to write to block number the third block, so block number 2. Or block number 1 is the first. So let's do disk write, and we give it the dd, and then we have the memory address, which is our block. And this is the block number, let's say the second block. Let's also see if we can get a return value from this. And by the way, when we detach, we should also close the file descriptor. So close ddfd. All right, let's see if this compiles. No. Expected identifier order for that. 34. Did I miss any of the parentheses? No, I think it's right. No? Oh, I forgot one of these. Okay, that's better. Left-hand operand of comma expression has no effect. should have a parenthesis here. So let's see, this is connected to that. This is connected to this. We don't need this. Okay, it compiled. Let's see what happens. X equals to true. So that should mean that the write operation was successful. Let's go into our drives and let's do a hex dump of this thing. It wrote one single byte. Block size times B. And it should read the entire block size. All right. Is it the right location? 400. 1024. So the first block is 0 to 511. Then we have 512 to 1023. So this is the third block. And what did we give it? We give it a 2. So 2 times. We should take this number minus 1. When we do the seek. So block size times B minus 1. Wait a second. There's probably not something wrong with this. Maybe the initialization only created one 0x90. That's probably it. Let's write some function which does this instead. Like so. And let's try this again. X equals to true. That's more like it. So first we have zeros all the way up to through the first and second block, and then the third block contains all these 90s and then the 0 bytes. So this works. Pretty nifty. Let's see if the read does as well. So we'll change this to read, and let's print some byte from this block. Let's say this will be the char value of BL 500. And this time the block will be 0 initialized. So let's see what we get. X equals to true, and we get a 0x90. Alright, so now the disk emulator is complete. We are able to read and write any block, we can attach and detach, and we can print information about the disk. And that is all we need for the disk emulator. So in the next episode we will be able to start creating our file system, which will be an interesting and exciting task. If you like this episode, please like and subscribe, and don't forget to hit the bell icon so you get a notification when the file system episode will be released. Thank you for watching, and thanks for today.